Okay. Okay, can you see the slides on the screen? All right, thank you. So let's move on with, so previously we've discussed all the processes before the front end, and we're still at the front end. So we've discussed from the wafer, the epi, and then the SDI, and then well formation, and finish off with well annealing before, and now we're coming to the gate formation. Remember all the modules that we have when we talk about process integration. So now we're going to form the gate on the device, okay? So we're going to start with growing growth of sacrificial oxide or SACOX. So in this case, a thin 250 angstrom or 25 nanometer oxide layer is grown to capture defects in the silicon surface. So we're going to grow. So remember, when we talk about grow, then that means we're going to use thermal oxidation, right? Thermal oxidation, a very thin one, 25 nanometer of oxide growth on the structure. Then, so remember the goal here is to capture defects in the silicon surface. And then the next step will be to remove, right? You grow and then you remove because you want to remove all the defects. And then that's why you call it SACOX, right? Sacrificial oxide. It is grown in order to be removed eventually, okay? Duduk sekejap ya. So remove SACOX. SACOX is immediately removed in a wet HF solution. Wet HF. Hydrofluoric acid is used to remove oxide, okay, silicon dioxide, leaving behind a clean silicon surface because you have captured the defects, removed already, together with the SiO2 SACOX, right? Then grow gate oxide. Okay, this is the oxide layer under the gate. Okay, we've mentioned a couple of times about gate ox, and this is the gate ox that we're going to grow. So grow gate ox, this is the most critical step in the process. A very thin layer, 20 to 100 angstrom or 2 to 10 nanometer, depending on the technology node. It can be very, very thin now for the latest technologies. A very thin oxide layer is grown that will serve as the gate dielectric for both transistors. Gate dielectric for both transistors. On the P side, PMOS and NMOS. So it must be extremely clean and grown to a very precise thickness, plus minus 1 angstrom, okay, or plus minus 0.1 nanometer. Okay, so that means if you look at your SPC chart, you punya plus minus can only fluctuate within this, plus or minus 0.1, 0.1 up, 0.1 down. The target is here. Say your target is 2 nanometer, for example. So you can only afford to fluctuate between 1.9 to 2.1. Okay, because the plus minus is only 0.1 nanometer. Okay, so a very small fluctuation means your growth has to be very precise. Tak boleh kurang, tak boleh lebih, So this is gate ox. So then we're gonna get your gate ox there. The clean, the yellow color. Then the next step, deposit polysilicon. Right, polysilicon will be the gate on the gate ox. Okay, polysilicon will be the gate on the gate ox. Polycrystalline silicon is deposited using CVD to a thickness range of 15 to 13,000, 1500 to 3000 angstrom. So that's about 150 to 300 nanometer. if you want to use in nanometer, thick. So right, you can see here that the deposition is blanket. Apa maksud blanket? What is the meaning of blanket here? Anyone? We discussed before. Apa maksud blanket? Anyone? Or layer lagi? Layer lagi? Any other? What do you mean by blanket deposition? If it's not blanket, then what? Okay. Faris said or layer, coat, right? What's a blanket? You deposit, but then you deposit. How do you deposit? You cover semua all throughout the surface. Okay, so that is meant by blanket. You cover the whole surface uniformly. Yes, uniformly. The whole surface. So if you spin coat blanket, then the whole surface. If you deposit blanket, that means the whole surface is deposited with polysilicon, right? So 150 to 300 nanometer of polysilicon deposition, polycrystalline in this case, by CVD. Next step. Tengok kita apa ni? So pattern. Next step will be the patterning. Pattern photoresist to define gate electrodes. So remember, when you do the lithography, what you want to do is you want to define your patterns. You want to do patterning and define area to be exposed and to be removed, right? So that means you want to pattern your features, whatever your features are, but you want to do the patterning. That's why sebelum litho we do blanket, then during the litho you define the areas that you want to keep and areas you want to remove. So that's the rule of lithography. Pattern resist to define gate electrodes. Remember, the gate is not blanket, right? The gate is supposed to be at certain locations. If you look at CMOS configuration, this is the most critical patterning steps in the process. Okay, sebab apa dia critical? Because the gate is the one that controls the switching. Okay, so control the switching means what? Speed. Control the speed of the device. Okay, if you're talking about switching, then you're talking about gigahertz. Berapa gigahertz boleh pergi is defined by the gate. A precise sizing of the polygate length is first order determinant of transistor switching speed. Slow ke laju ke depends on this. Okay, the highest technology patterning system are DUV. In this case, when the integration was very simple back then. Currently you're talking about EUV. Okay, EUV. So along with thinner than normal photoresist due to critical nature of the layer. Now it's even thinner than DUV, right? So now you do the patterning of the resist. So in this case, you can see that the resist already patterned, right? But before this, you should expect a blanket spin coated photoresist throughout the surface. And then say if the resist is positive, is a positive resist, then you want to expose, if the resist is positive, you need to expose here. Semua ni you have to expose if the resist is positive. And this is the areas that you want to mask, you want to block. Okay, because the exposed areas will be soluble and then gone. So you'll be left with these features that you want to define the gate. So in this case, the photoresist yang remaining ni kena unexposed lah. If you're talking about positive resist. If you're talking about negative resist, then you're talking reverse. So you define the resist, and what happens? Tengok ni. Then etch polysilicon and strip resist. So remember, the resist is there just to define the patterns on the device. Okay, the resist is not there forever. It's just there as a medium to define your patterns. So that's why you have to then etch polysilicon. So below you've got the resist here, and then your orange color, this polysilicon is all exposed, right? And these areas are masked. So you then will etch the exposed polysilicon. You can see that the polysilicon are all removed. Semuanya remove. The polysilicon all etch. Tinggal ke area yang protected by the resist only, right? So the moment you have removed the etch, you have etched the polysilicon, then you should be left with something like that. The resist on, and then you strip off the resist, and then you're going to be left with polysilicon gate on gate oxide. Okay, use etch polysilicon, strip resist, reactive ion etching using fluorine chemistry. Typically, this one uses SF6 gas. Fluorine chemistry ni pakai SF6. Usually silicon kita pakai SF6. Sulfur hexafluoride. Sulfur hexa 6. Right. Tak nampak dalam ni. SFCS, sulfur hexafluoride gas is used for the fluorine chemistry in RIE process. The complete formation of the gate stack. So then the gate stacks form. So now you've got this. If you zoom in this, you're going to get this, right? Now we have polysilicon gate on gate oxide on your well. Okay, di bawah ni well kan, N well, P well, depending on your architecture, but that's how it looks like. So now you've got the gate formation ready, or gate stack ready. Okay, gate stack here means you've got the gate on the gate oxide on your well. Then what else? What's next? We oxidize the polysilicon. All right, we oxidize polysilicon. A thin layer of oxide is grown. On top of the polysilicon to act as a buffer between polysilicon and subsequent silicon nitride layer. Then about silicon nitride next. Okay, but before that, you need to oxidize the polysilicon. You can see that the yellow color is formed throughout, right? Oxidation of the polysilicon. Next, source drain formation. So we've finished the gate formation already. So relate back to the modules that you're supposed to have in the device. So now we want to form source drain. Okay, you've got the well, but now we want to form the source drain. So let's see why and how do we form the source drain before you get your final MOSFET, right? Pattern the resist. To be able to form the source drain, you first have to pattern the photoresist for NMOS transistor tip implant. Okay, macam kita buat sebelum ni, you nak form the well, you block one area and then you open one area and then you implant one area, right? So we're gonna do pretty much the same thing, except you're gonna form a different kind of doping. So let's see. So pattern the resist. So in this case, let's revise. If your resist is positive, in the lithography, where would you expose? On the left or on the right to be able to have this pattern? If your resist is positive and you're running lithography to be able to produce this pattern, the red resist, would you expose your resist on the right or on the left of the schematic or of the device now to be able to end up with this feature? Expose mana? Kiri ke kanan? Where would you run your exposure? When you not form your mask, be able to get this feature. On someone, how do you expose your resist in order to get this. Faris, how about Faris? Where would you expose your illumination from the scanner in order to end up with this resist? On the left or on the right? Faris? Right? Okay, kenapa? Kenapa right? Why do you expose on the right? Why would you expose on the right? Anyone would like to add on that? Kenapa nak expose on the right? Or anyone would expose on the left? Expose right. Okay, Sakina said expose right sebab soluble. Yes, right? You want to expose on the right because you want to make the resist to be soluble and eventually gone. Okay, eventually gone. Remember when you run the CED in lithography, you have to spin code semua. Mana boleh spin code tempat tertentu kan? You have to spin code the whole thing. But then what differentiates your features will be on during the E step, exposure step. So in this case, since the resist is positive, and for positive resist, the exposed areas will be soluble and eventually removed, and hence not on this picture. So you want to expose on the right side so that the resist is soluble and then removed during the development process, CED, right? Removed by timah during the development process, and then you're going to be left with patterned resist on the left to be able to do this pitch, right? So now you end up with patterned resist on the left. So what we're going to do next is now you want to do a transistor tip implant. What is that? NMOS transistor tip implant, a very shallow, low energy, right? A very shallow, low energy. If you go deep, if you want to go deep and you want to go for high energy, if you want to go medium, you have to use medium energy or middle energy, right? So in this case, you want to go very, very thin or very, very shallow, very thin. You can see here, oops, very thin, right? Very thin tip, shallow, yeah, shallow implant, very shallow, low energy, hence low dose implant of arsenic, in this case, arsenic, right? N type begins the formation of the NMOS transistor source and drain, right? So tengah ni dah diblock oleh gate and gate oxide, right? Gate oxide covering the gate or wrapping the gate, but you implanted a very shallow tip on the left and on the right, forming your source and drain. Okay, the tip will serve to reduce hot electron effects near the gate. Okay, hot electron effect near the gate. So apa hot electron ni? High energy electron near the gate. So let's see what's next. So you form the tip implant. Then we strip the resist. Done. We strip the resist. The moment you've done the implantation, you strip the resist. And guess what's next? The pattern on the right block. Okay, pattern on the right. So we just reverse the process set by Faris and Sakina just now. So you do the very same CED, another round of CED. So you tengok kat sini, bila nak pattern je, you have to go back to litho and then you etch and you go back to implant. So the process flow is very messy, if you like. So it really depends on what do you have to have on the device, okay? So it doesn't necessarily have to be a fixed flow because it really depends on what you want to fabricate. So in this case, if you're talking about positive resist, you have to pattern on the right, and to be able to pattern on the right, you have to expose on the left, okay? Expose on the left, reverse process that you discussed. Expose on the left so that the left resist will be soluble and therefore gone and exposed. Exposed means area device to you dah exposed for the environment so that you can do the tip on the left hand side. Then you have done the tip on the right. So the right is done. Now you protect the right because it's done already. Now you open the left so that you can repeat the very same process for PMOS transistor tip. So you repeat the same thing except you do with opposite polarity dopants. A very shallow, low energy still, somehow, low energy, low dose, but this time is instead of arsenic, you use Bf2 ions. Boron, boron because you want to form the p-tip, p-type tip. Formation of PMOS transistor source and drain on the left and on the right, and then the gate mask the central area. The tip will serve to reduce hot electron effects near the gate region, same thing, except it's reversed. What's next? They will strip off the resist somehow. Okay, the moment you strip off the resist, you can see that now you've got your gate encapsulated by oxide, and then you've got your source and drain on both PMOS and NMOS transistors. Okay. Next, deposition of silicon nitride. Okay. Deposition of silicon nitride using CVD with thickness of about 120 to 180 nanometer, or 1002 to 1008 angstrom in thickness. So you can see, the mechanism, the constraint, the corner, the rounding effect, everything. So this will be happening in the process, right? So CVD of silicon nitride. So why silicon nitride? You can see is blanket. Again, blanket is a blanket deposition. So that means it's deposited throughout the surface, across the whole surface. Okay, blanket somewhere here. Next, ready? Next, blanket deposition. Then you etch nitride. You deposit nitride, then you etch nitride. And you deposit. You're not etch point eventually. It's just that you want to keep the nitride as the spacer on the side wall only. Tempat semua nak remove. To be able to do that, you have to etch nitride to form spacer side walls. So these are called spacer side walls. Using a carefully controlled RIE etch, the thin nitride is removed from the horizontal surfaces, but the side wall remains. Okay, these side walls will precisely position the implants that form the transistor sources and drain. Okay, sekarang the spacer side walls form. Next, litho lagi. You go to litho again. Same thing. If you use positive resist, you want to pattern on the left. So that means you have to expose on the right, develop on the right. You're going to be left with resist on the left. Okay. If you're talking about negative resist, you're talking about the opposite way. Pattern resist for NMOS transistor source drain implant. Tengok apa pula jadi apa ni? Then you implant arsenic. The shallow high dose implant of arsenic ions completes the formation of heavily doped, right? Remember here two things. If you talk about implant in this case, you're talking about two things. The first thing is the depth of the implanted layer, the depth of the channel, shallow or deep. Okay, so that depends on the energy of the implanted, low energy, middle energy, high energy. The second thing that is also important is the dosage. Dosage will control the doping level. That's why when you use high dose, it will end up in heavily doped layer, right? If you use low dose, then it's going to dope with a lightly doped layer. Medium, then medium, right? So typically high dose, heavily doped, you're talking about 10, 17 above, 10, 18, 10, 18 at least. Heavily doped NMOS transistor source and drain. Okay, tengok tadi, if you compare this with this, just now we had the tips of the channel tip. Sekarang kita pakai low energy high dose. You will add on to that, right? You will add on to that. So you add the tip. The spacer shadows the implant near the gate region. Okay, spacer ni the shadows gate. So that's why you can see here the layer down here doesn't expand. Sama aja. The depth of this layer is not expanded because the spacer shadows the implantation process. So that's why you can only get your channel deeper beyond the spacer. Okay, on the left and on the right of the spacer, you're going to get deeper due to the new implantation process. So, well, this is not default, and it really depends on what sort of designs that you're supposed to fabricate. It's not like a single way to do things, right? It really depends on the device configuration, device design, process flow, everything. Next, strip off the resist. Done. So guess what's next? The reverse process, right? Reverse process. We now pattern on the right. And if the resist is positive, you have to expose on the left, expose scanner, scanner expose on the left, develop on the left, and then your resist will be left on the right. You then repeat the same process with the opposite polarity dopants. So let's say the shallow high dose, again, two things. Shallow high dose, BF2 ions for p-type to form heavily doped PMOS transistor source and drain. Again, the spacer shadows the implant near the gate region. So you're going to get deeper channel beyond spacer side walls. Okay, the spacer will block the implantation process quite successfully. Okay, then you're going to produce the very same thing like on the right. Then we'll strip the resist just like what we had done now. So now you end up with lightly doped tips, masked by the spacer nitride side walls, and then you're going to have deeper junction beyond to the right and to the left. Right? Strip the resist and anneal implants. Use RTA, rapid thermal annealing, to virtually eliminate dopant migration in the shallow source and drains. Electronic devices are now completely formed. So now form the basics of the device. All that remains is to connect them together, right? So now you've got the gate, you've got your gate oxide, you've got your source, you've got your drain, you've got your well, you've got the silicon substrate. So you've got your basic MOSFET structure, okay? But are they now connected? They are not yet connected. Tak ada connection, eh? So you just ada the front end only. Back end is for connection. Remember we talk about process integration earlier on. We talk about metal 1, VR1, metal 2, VR2 sampai the contact, contact. Okay, so you are pretty much done with the front end. Pretty much. So let's see what's next. Strip off surface oxide. So remember last time we grew the oxide, the thin oxide on the gate. We now have to remove the oxide. Okay, tengok kat sini. You dah remove the oxide. Strip off surface oxide. A quick dip in HF. Again, HF is here to remove or to etch SL2. How about the chemistry of HF? Is it isotropic or anisotropic? Iso or aniso for HF etch. To remove this oxide, to expose bare silicon in the source, gate drain. Iso or aniso? ISO, right? Isotropic process. Yes, isotropic process. So it's an isotropic etching process by the HF. Okay, now remove the oxide. Okay, done. Oxide is removed. Next. Okay, sekarang kita nak start ke backend. So remember last time I told you when you do fabrication, even though the fabrication is considered front end industry, you will still have FE and BE. So, kalau you masuk fab, then normally you will use this front end and back end. FEBE. Kalau you nampak job description cakap FEBE tu front end back end lah. Walaupun dalam wafer fab industry. But if you talk about the whole industry, then front end refers to fabrication, back end refers to the packaging, the testing, the packaging, the product level, chip level and product level. Tapi if you talk about the fabrication, the wafer fabrication itself, dalam tu pun dia bahagi lagi front end and back end. Front end is mainly all this, front end, and all the next steps that we're going to discuss will be considered back end. Titanium, silicide, IMD, metal 1, VR, until top contacts. So next, deposition of titanium. Now we're starting our back end in the front end industry. You use a sputterer or sputter to deposit a thin 20 to 40 nanometer layer of titanium across the entire wafer. Again, is a blanket process using sputtering. Would you go for DC or RF sputtering in this case? Anyone? Would you go for DC or RF sputtering to deposit titanium? Why RF? Hazik, can you use DC to deposit titanium? Is titanium conductive? DC ke RF? DC, kenapa DC, Faris? Metal. Okay, metal you can do on DC, okay? You don't have to go for RF. Well, you can, but you don't have to. Unless you can have better control or something, then you can go for RF. If I'm talking about titanium dioxide, for example, would you go for DC or RF? Right, why RF? Insulator, yes. If you're depositing insulator, not conductive, you have to go for RF. RF. So metal you can do with DC. But if you do metal on RF, it can still sputter. Cumanya dia tak ada limit, sebab dia tak ada limitation of conductivity. Because it's conductive after all. If it's not conductive, then it's a special case. You have to go for RF. Okay. Kalau tak, kalau metal, either one is fine, but DC will be good enough, right? But it's not wrong to do RF. So now we do blanket deposition of titanium, blanket on the entire wafer, 20 to 40 nanometer. So what's next? Kita tengok layer to layer, slide to slide. Jadi, titanium silicide formation, what is this? Rapid thermal processing in nitrogen, RTP process, rapid thermal processing in nitrogen at 800 degrees Celsius causes the titanium to react with silicon. Okay, titanium will now react with silicon, okay, forming titanium silicide, where the two are in contact. So it forms alloys of titanium and silicon. That's called titanium silicide. In other areas, the titanium is unchanged. This process perfectly aligned with silicide, the silicide to the exposed silicon, and this is called self-aligned silicide or salicide. Okay, self-aligned silicide or called salicide. Salicide boleh lah. Salicide. So you can see here where the silicon is in contact with titanium, you're going to form silicide, right? Those with the areas that are not in contact will not have any reaction. Therefore, they will remain as titanium. Okay, the purple color ni semua reacted. Dah react dengan silicon, and you're going to form salicide. Okay, self-aligned silicide. Next, so apa jadi? So those with yellow color, sorry bukan yellow, purple color, dia dah embedded, dia dah masuk and react. Therefore, dia dah macam lock lah, it cannot be removed anymore. But the blue ones, the blue areas will be removed because they are just sitting there, no reaction. Therefore, you're going to then etch the titanium that did not react. Okay, etch titanium, the unreacted titanium is removed using wet etch in ammonium hydroxide plus hydrogen peroxide. NH4OH, ammonium hydroxide plus hydrogen peroxide. The titanium silicide remains because already have reaction, forms alloys. TiSi2 titanium silicide provides an ohmic contact between silicon and metal. Okay, ohmic contact. You need to have this ohmic contact between silicon and metal for current conductivity later on. Okay, form metal contact sekarang. So you want to have, you need to have ohmic contact between metal and silicon, and that is enabled by the titanium silicide. Next, 10:41. So let's go for like 10-15 minutes before you stop for the second session. Right. So now you've got your titanium silicide embedded, okay, already alloyed with silicon. Next, now we're going into the back end. Deposition of BPSG. Apa BPSG ni? Silicon dioxide dope with small amounts of boron and phosphorus. Okay, silicon dioxide dope with small amount of boron and phosphorus. It's basically silicon dioxide, but the dioxide, the SL2 is dope with boron and phosphorus. That's where you get your B and P. Silicon dioxide dope with to enable firm reflow and to gather contaminants. Kenapa kita buat this gather? Remember last time we talked about gathering process, remember? In grade 6, I think. Gathering. Or is it in this course? Oh yeah, we also talked about gathering in this course earlier on. Kenapa kita buat gathering? Why do we introduce gathering process? Ingat tak? Anyone? During the first part, earlier on. Why do we gather? Jawapan ada kat slide tu. You want to gather contaminants, right? You want to collect contaminant dekat passive area kan? Then you're gonna remove the defect from the active area, and they're gonna be located at one place and eventually removed. So that's called gathering, right? Gathering, you compose all the contaminants and defects and everything. By deposition of CVD, using CVD, the approximate thickness is about 1 micron, so that's why you can see that it's relatively thick in comparison to the previous layers. So 1 micron. This layer will electrically insulate the devices from the first metal layer. So that means we're gonna have the first metal layer soon, but this layer will insulate your first layer of metal with your active device down there. So bila you tengok nanti bila we complete the whole integration, you can see that the active device duduk kat bawah sekali. Yeah? And the layer macam kondo later on, I want to see 1, 2, 3, whatever tu, is just interconnection. Tapi active layer, the gate and gate aux and the switching, semua kat bawah sebenarnya. Yang atas yang complicated semua contact je. Right? The switching is all down there. But of course, you're gonna have some contribution from metal conductivity and switching and many more factors contributed by the backend as well. Backend as in the metal contacts and the VRs and so on. But then the key, the heart of the device is down below. Okay? Sekarang tak nampak lagi sebab kita nampak gate tu masih kat atas lah. So later on, you're going to see that it's just down below and you're going to have like top metal after 7, 8 layers of metal and VRs, right? So this BPSG, boro-phosphosilicate glass, if you like. So boron, phosphorus, dope, silicon dioxide, BPSG, boro-phosphosilicate glass will electrically insulate the metal contact, the first layer, with the active device. So let's see what's next. We now polish. Okay, kita polish pakai proses apa? CMP. Okay, polish, remember the polishing process, the pad, and the slurry, and the cleaning, and the flattening, and the planarization. CMP, chemical, mechanical polishing. Polish and planarize. When you add the features, and you use CMP, you will planarize, okay? Tadi kita ada feature kan? Kita ada ni feature, you want to cut this off and planarize, and you're going to end up with that. So that's done by CMP to achieve a flat surface on the BPSG layer. If not remove the bumps on the surface from the underlying topography, will cause a problem for the subsequent lithography steps and degrade metal step coverage. So kalau you ada bump, so later on you still have to pattern your metals and everything, and the VRs. Kalau ada bump kat bawah, then we discussed last time about if your defect and stuff, that will alter the depth of focus and the resolution and pattern collapse, all the stuff. Those will affect the quality of the next lithography steps and the next etching and the next deposition. Okay, and that's why you have to planarize the surface. Okay, so let's go for another 5 more minutes, I think. Okay, then now we're talking about the first interconnect. Okay, remember the active device will be down below. Sekarang kita nak tengok the metal contact. So to be able to do that, you have to pattern the resist to define contacts. Remember, the resist is there to pattern. Okay, contacts are openings in the BPSG layer enabling electrical access to device. You want to have access to device, but then you don't want to open because you have to electrically insulate the interconnects and the active layer properly. Okay, so contacts are opening in the BPSG layer. You nak open the BPSG ya. BPSG nanti kita nak korek ya. You want to dig this, you want to etch. Tapi sekarang kita kena define the area to be etched first. Okay, then you pattern, then you're going to get this kind of pattern. Then sama dia punya discussion, if the positive resist, then you have to expose all this and then develop later on. And these areas are all exposed. Next, you etch, okay? You etch the contact. So it's called contact etch. Tadi contact contact litho if you like. Kalau dalam process flow tu dia panggil contact CED. Okay, then next step dalam process flow, kalau tengok spec nanti lah kat sejarah for example, you're going to see contact CED, contact etch. So this is contact etch. This one contact CED. Contact etch, then you carefully design the RIE process using fluorine chemistry to achieve vertical sidewalls. You etch the exposed areas sampai you reach the silicide, titanium silicide, remember? Si2, the purple color, the alloy, sebab kita nak form ohmic contact. So that means you gonna put your contact dalam ni nanti, tanam contact dalam contact ni lubang lah. Contact ni is the hole lah basically, right? And the resin will be removed. So now you have to etch carefully sampai they reach titanium silicide. Jangan over etch, over etch scrap, right? So maknanya dia punya etch depth will be super critical for you to stop. Kalau you stop before you finish, then you're gonna be left with BPSG lagi lah. BPSG remaining kalau you etch tak habis. Then you're gonna put your contact on oxide and habis lah, tak dapat ohmic contact lah because you sit on insulator, right? So you have to etch just nice to reach the depth of silicide, right? Then you strip off the resist. Strip off the resist, and you're going to be left with pattern BPSG. Remember, we pattern the resist here in order to pattern BPSG. Okay, macam kita discuss hari tu soalan test kan? Soalan case study, I think. How do you pattern, soalan test, how do you pattern SiO2? So you have to pattern the resist first in order to pattern SiO2. But your goal is actually to pattern SiO2. Resist is just a medium and intermediate step for you to do the patterning. Then the resist will be eventually removed. So exactly the same like this, exactly the same every single time, right? So you pattern the resist here to be able to pattern BPSG. Then we remove the resist, you etch the resist or resist etch. Then you're going to be left with pattern BPSG. Next, okay, satu lagi, then we stop. Right? So you strip off the resist. Then next step, titanium nitride deposition. Right? Tinitride. We normally call it tinitride. Tin tinitride. So sputtering process is used to deposit tinitride about a thickness of 20 nanometer. This layer will help the subsequent tungsten layer to adhere to the oxide. This is for addition. Okay? Subsequent tungsten layer to adhere to the oxide. So we deposit blanket as well. So you see here, you still have to sputter inside. Your conformality is equally critical. So they can cover all the depth and the shadowing effect that we discussed before. Make sure you can cover the minimum thickness, and especially on these edges, you need to make sure that there's no breakage. Kalau tiba-tiba breakage, then your tinitride will not be sitting on the edge. You have to make sure that the whole L shape kat sini ni is well covered, right? Then what's next? Tinitride is done. Okay, one more. Sampai CMP lah, then we stop. Then tungsten deposition. Tungsten is chosen because it deposits conformally via CVD. Tungsten W, CVD tungsten to fill the hole. Okay, tungsten will be used as the contact. Or kita panggil dia plug, W plug. Plug macam contact. tungsten plug. Kita panggil dia plug. The moment you contact edge, you akan masuk tungsten as a plug. Plug ni dia akan connect between layer 1 to layer 2, layer 3, and layer 4, right? So it will fill in the hole. So tungsten ni dia akan fill in every hole. So the thickness must be half at least of the diameter of contact. Then what's next? We remove the tynetite. We polish the tungsten, remaining tungsten. Kita remove yang atas. CMP is used to remove the surface of tungsten. The remaining tungsten forms plugs. Okay. Yang mana you letak metal dalam lubang ni, contact ni semua, we call them as plugs. The surface titanium nitride is also removed. Right, so let's just stop. We'll stop here first, then we're going to continue with the metal 1 deposition. Okay, sekarang kita dah connect. Okay, when you're done with this, what you have now is actually a metal connection, tungsten, by the tungsten. You already established your connection between the silicide and to the next metal contact. Okay, so maksudnya you dah ada metal to connect your device through the silicide, masuk through tungsten plug to the next layer. Next layer will be metal 1. You can just imagine a metal 1 and then you're going to have insulator in between, metal 2, then plug, then contact, then plug in between, metal 2, and you repeat. You buat contact formation, then contact edge, and then you dunk tungsten depth, and then you polish tungsten, and then you prepare metal 2, and then you repeat sampai metal berapa? 7 ke 8 sampai ke top metal. So you're going to repeat the very same process with, of course, slightly different parameters, but then the basics are the same, right? So let's just stop here for a while and 10:53. So kita berhenti about 10 minutes, 10:55, let's say 10:55. Let's continue at 11:05, okay? 11:05, yeah? Any questions so far? Ada soalan? No? Okay then, so I'll see you again 11:05, yeah? Bye-bye, take care. Right, let's continue. Can you see the slides on the screen? All right, thanks. Right, so let's move on. So as I said is now, until now you have got your uh, tungsten plug connecting the titanium silicide, okay, the titanium silicide to the next metal layer, which is metal one. So now let's move on to the next layer. Right, so the next layer is about deposition of metal one, the blue color here. So deposition of metal one, each interconnect layer is actually a sandwich of different layers. So it looks like a single layer. So it looks like a single metal. Wait, kenapa hilang? Hold on, yeah. Full screen. Alamak. Let me go full screen again. Okay, nampak ke? Tadi ada problem sikit. Nampak ke full screen? Right, okay, thank you. So metal one, it looks like a single layer. Sebab color dia nampak biru sama. Looks like a single layer, but is actually formed by a couple of layers in between, right? So the sample is shown below. The films are deposited by sputtering. So this metal one consists of, kita tengok kat sini, the first layer, the down one, the below, the most below one is titanium, 20 nanometer, 200 angstrom for electromigration purpose. We're going to see electromigration in the next topic before I finish the course. And then the second layer is titanium nitride or tinitride, 500 angstrom as a diffusion barrier. And then the third layer is aluminum copper, alloy of aluminum copper as the main conductor. So that's about 5,000 angstrom or 500 nanometer. So it's quite thick in this case. And then the final layer will be titanium nitride for ERC. Okay, titanium nitride is about 500 angstrom. So that forms those layers form metal one. Next, so now we're going to pattern the metal one by first patterning the resist. But the goal is, remember, to pattern the underlying layer. Okay, the layer below the resist. The resist is just there to to enable the patterning process. Okay, so depending on the positive or negative resist, in this case, if the positive resist is used, then you have to use your scanner to expose the open area so that they are all removed eventually. Then the next step is to etch. Okay, so tadi metal one, if you like metal one, ni kita panggil metal one deposition, metal one dap. Okay, kalau dalam proses flow, we normally call it as metal one dap. Or okay, the next step will be called as metal one CED. Okay, ini proses flow Tapi nanti bila kalau you masuk Siltera ke Infineon ke, kalau you baca spec tu, you can relate right away. Metal one CED, metal one etch, metal one CVD, or metal one DAT or something. So this would be called metal one etch. Sorry, metal one CED. Sebab you nak pattern the resist. And the next step will be called metal one etch. Okay, where you etch the metal. Okay, you etch the metal. Now the metal is patterned more or less, right? It's patterned. So etch metal one, RIE utilizing chlorine chemistry. Multiple etch steps are required. Multiple etch steps are required in order to, due to multiple different layers. So due to multiple layers, then you need to use multiple etch steps, but you know, etch different materials within the metal one. Okay. Then only you're gonna have your metal one etched. So next step will be to remove the resist. Okay, remove the resist or strip the resist then your first interconnect layer is formed or is completed. So you're now left with metal 1 interconnect. Okay, metal 1 interconnect is ready. So next step, what is it? IMD. Okay, macam BPSG punya konsep. But then we call it as IMD. Kenapa kita panggil dia IMD? So IMD second to end. End mean as many as 8, depending on the device configuration. So this is called IMD1. Undoped silicon dioxide is deposited using successive CVD deposition process. Okay. Right. So undoped silicon dioxide is deposited using successive CVD deposition. So that's called IMD. Intermetal deposition. IMD to intermetal deposition. Intermetal dep, IMD. Okay, because this will be deposited between metal 1 to metal 2, 2 to 3, 3 to 4, 4 to 5, so on and so forth, right? Intermetal deposition, so IMD. So IMD1 will be separating metal 1 and metal 2 using CVD and edges to achieve filling between metal lines. Approximate thickness about 1 micron, relatively thick. So this layer will insulate metal layers from one another. So this will insulate metal between metal layers, and your BPSG will insulate between your active device to metal 1. Okay. And ready? You planarize. Okay, planarize pakai CMP. CMP is used to achieve flat surface, to remove all the bumps. If not remove the bumps, will affect the next layers. Next, you pattern the resist. Okay, kenapa kita pattern resist kat sini? Because you want to define vias. Okay, in between metal 1 to metal 2, 2 to 3, you call via. Contact tu, hole tu you akan panggil dia sebagai via. Okay, so multiple via you call vias lah, but then it's called via. Metal and via, metal and via. They'll be in pair until you complete the device. Vias are contact openings in the IMD layers, enabling electrical access between metal layers, metal 1 to 2, 2 to 3, 3 to 4, and so on and so forth. So you pattern the resist to be able to pattern the IMD. Okay. So you pattern the resist. So this is called IMD. You get this type if you like, called IMD CED. And then IMD-etch. Okay, you carefully design your RIE using fluorine chemistry to achieve vertical sidewall. So you etch your IMD and then you strip the resist off. Strip the resist off. Done. Okay, strip the resist sama macam tadi. So you're gonna repeat the very same process pretty much from layer to layer. So now you have got your VR. Ini semua ni is called your contact opening is called VR. VR. Okay. Then you deposit tungsten, tungsten dep. So if you like, this one is called tungsten or tinitride and tungsten dep. Same as for the first interconnect. Sama macam plug tadi. So you just repeat the process second time. Then you polish the tungsten, remove tungsten. Then you're gonna be left with tungsten via plug. Any tungsten contact plug. Technically same thing. Cuma dia punya is a bit different because the first one down there is between your device to metal 1, and the remaining dekat atas nanti will be via plug because they are separate. They are connecting metal layers, right? 1 to 2, 2 to 3, 3 to 4. Next, you deposit metal 2. You repeat balik same process just like metal 1. So subsequent metal stack will be similar to metal 1, but tend to increase in thickness and width as their runs are longer and they carry more current. So as you go up the stack, metal 1 to 2, 2 to 3, 3 to 4, 4 to 5, you can extract more current. So then your thickness need to increase as well. And the width has to increase as well because they need to be more capable to carry more current. Okay, metal 1. Then what's next? You pattern. Okay, pattern the metal 2. Sorry, metal 2 is deposited, and then you pattern the metal 2. Interconnect edges of metal layers are patterned perpendicular to each other to minimize inductive coupling between layers. So the other issue inductive coupling between layers. So you have to pattern properly. Then you etch. Tadi metal 1, ni metal 2 CAD ya. So in the process flow, if you're an integration engineer, for example, you're going to name this process step as metal 2 CAD. Okay. So the next step will be called metal to etch dalam process flow. So when you read the spec later on, if you join Silterra ke, Infineon ke, if they run on the same configuration, then this is called metal to etch, metal to etching. You etch metal 2 using a chlorine chemistry. So you need multiple steps due to the multiple layers in the metal 2, macam metal 1 tadi. Then you will strip off the resist, sama. Lepas you litho, you have to etch. Litho etch for every single layer. Then you're done with metal 2. Your metal 2 is completed. What's next? Passivation. In this case, the configuration is made simpler. So kalau in this case, deposition is already, no, the passivation is done at this step because it's designed to have up to metal 2. Okay. Kalau you ada up to many more metal layers, you can check later on. Kalau you ada up to metal 8, for example, and you're going to repeat the very same process. You akan buat macam tadi ya, reverse process. Oh, sorry, the reverse process. Okay, let's say you are at metal 1. Okay, your next step will be IMD2. Kalau you ada, sekarang just imagine this slide for your metal 1 is actually your metal 2. And you're going to need metal 3, for example. Then you're going to need to deposit IMD2. Okay, IMD macam ni juga. Then you planarize your IMD2. Then you pattern your IMD. Then you etch your IMD2. And then you deposit tungsten in your IMD2. And then you polish your tungsten in IMD2. And then you deposit your metal 3. Okay. Then you're going to need to do the same thing. You pattern your metal 3. You etch your metal 3. And then you strip off the resist. You're going to be left with metal 3. Then kalau nak buat metal 4, then you deposit IMD3 pula. IMD3 and then buat apa? You polish and you etch and then you plug and then you deposit metal and then you get metal 4 and so on and so on and so on and so on. Okay, nanti try search. Now, okay, let me just give you 1 minute. You try to search how many metal layers you have in advanced transistors. So, cuba search online sekarang. Then you can share in the chat box. How many metal layers do you have? How many metal interconnect or the metal layers do you have in advanced devices, advanced transistors? Cuba search. And you can also see the Google image if you like. Try to see how complicated it is. Next, you share in the chat box. Sekarang kat sini saya just explain up to metal 2 because just to illustrate, sebab metal 3 onwards is just the very same process repeated until you get your final layer. Cuba check. Has someone found any numbers? How many? Saya pernah search juga. How many metal? Wow, 10 to 15. Right, ada lagi? Metal interconnects. Ada lagi? Siapa yang jumpa tulis ya? In advanced transistors, perhaps. Ataupun in advanced MOSFET pun boleh. Ada lagi other than go? Siapa lagi jumpa other list? Metal interconnect. Ada lagi? Other than 10 to 15, do you find any? 7 metal layers, Joria. Okay, 7 metal layers. Ada lagi? 7 metal layers as well as 8 are common for 28 nanometer. Yeah, that is very specific. Good. So for 28 nanometer technology, then we are talking about 7 to 8 metal layers. So that means if you are talking about this 28 nanometer, for example, if you get 28, then we're talking about metal 1, metal 2, metal 3, metal 4, metal 6, 5, 6, 7. Then I think 6 and top metal. Top metal will be your last layer. Then kalau 8, then metal 7, then top metal. So in between, you're going to repeat the very same thing. IMD2, IMD3, IMD4, IMD5. Then you etch You get the VR, you plug, you planarize, and then you deposit the next metal, you pattern the metal, you blah blah blah. Okay, same process. Ada lagi, ada layers. Interconnect. Ni saya jumpa ni something very. It depends on the device. To be more specific, breaking 2 nanometer barrier. Hold on, let me see this. Copper. Ni kalau copper technology, you can see the image. You can see the image. Those oranges, bukan oranges, orange color. Okay, you can see this camera. Yeah, it's a stack of, I think about 5 or 6. Ni pakai copper damascene technology. It's another technology that you can use. It's called copper damascene. Okay, copper 1, copper 2, copper 3, copper 4, copper 5. Kalau tak pakai tungsten, right? Ada lagi jumpa yang lain other than 7 or 8? Resistor, ni ada satu lagi saya jumpa. 18 nanometer is quite complicated here. You can see the image here, tak nampak sangat. But the SEM there, it shows the stack. Stack though is the number of layers that you need to have. In this case, it's like 7 or 8, I think. Yeah, 7 or 8. Right? So 7 or 8 for 28 nanometer. Go yang you jumpa di 10 to 15 tu, any for each any specific technology? 10 to 15? Any specific technology? Is that for? You can write down here. Right. So assuming you are done with metal 2 ataupun ni dah metal yang high metal. So what you have to do next is the next will be preservation. Assuming this is like metal 7, metal 8. So your next layer will be preservation, close to completion. Deposition of preservation layer. There are many types of preservation: silicon nitride, oxynitride, polyimide, whatnot. So the purpose of this layer is to protect the completed circuit. So here is completed circuit. Bila you dah habis you design and you habis fabrication, you have to preserve, to protect, to encapsulate from scratches, contamination, moisture, exposure to the environment that can degrade the performance and stuff. So you have to preserve the top layer. In this case, just to illustrate up to metal 2, to make sure that you understand, right? But if you need up to metal 7, then repeat accordingly. Then pattern the preservation layer, right? You deposit blanket, and then typically done by CVD, the oxynitride, nitride, polyimide. Polyimide depends, I'm not sure. Then you pattern the preservation layer. The polyimide preservation is photo definable. Okay, then it can be lithography, can be done by lithography. Other preservation layers require a pattern resist layer followed by an etch step. Bond pad openings allow electrical access to the chip. So the role of the patterning at this step is to open an area or areas for bond pad. Bond pad ni hujung chip yang nak connect dengan wire kat ujung nanti. Kalau nak masuk dekat back end industry, you have to open the bond pad and then nanti hantar back end akan buat all the interconnects and everything. Okay, dia akan buat back end is more physical in nature. You can see the connection and all the stuff, but you have to provide the bond pad punya contact dulu before you can continue in the back end industry. Okay, sekarang front end almost done. So you open the bond pad and then next your bond pad is open. It's open. The areas for bond pad is ready. So then you complete the fabrication, the front end fabrication. But in this case, it's just a simple device up to metal 2. Okay. So if you're talking about 28 nanometer, for example, is now up to metal 7 or 8, or typically you call it as, if you're talking about 8 metal layers, then we're talking about metal 1, 2, 3, 4, 5, 6, 7, and top metal. Top metal 2 will be the final layer, but it has no number. Okay, so metal 7, then top metal. So that means you have altogether 8 metal layers, right? So if you're talking about 9 metal layers, then you're talking about up to 8 metal 8, then VR, then top metal, and a base, then preservate, then bond pad, right? So now let's review. So do you get the whole picture now of the integration from the epi formation, well, tip, gate ox, gate spacer nitride, source drain formation, IMD plug, metal one, via plug, metal IMD, so on, so forth, so on, so forth, sampai ke preservation. Is it clear now? Okay, let's recall. Okay, let's recall. Okay, kita review this one. Okay, let's review this one. Okay, what is this layer? This purple layer. Anyone? Okay, unmute yourself. Kita review ya. Habis ah. Yeah, almost done with this. We're gonna stop right after this. Tip, apa tu? What is the material there? What is the material that you use? The purple color. So for every layer, you have to know what is the material, how do you deposit, right? Titanium silicide, okay, silicide or self-aligned silicide, titanium silicide. Okay, kenapa you ada metal layer ni? Why do you need this layer? What is the material? Why is it for? How do you deposit? Kenapa you ada this layer? Let's recall. Habis lah, last about 10 minutes or so. Awal sikit lah ni. What is the role of this layer? What is the function of this layer? I think it's in the assignment 2 as well, if I'm not mistaken. Contact, be more specific. Is it the contact layer? Provide ohmic contact, okay? Be more specific, I say. Provide ohmic contact between your device to the metal contact. Okay, your metal contact in this case is the plug, tungsten tu. Tungsten plug. Dekat ni tiang ni. This is your contact. Okay, gray area is your contact. Ni plug lah, connecting between device and metal. Right? Okay, so titanium silicide. How do you get the silicide? How do you get the formation of silicide? So these are among the questions that are possible around this single layer alone. Macam mana dapat silicide tu? What did you do and what did you do next to be able to get the titanium silicide? Anyone? Do you get the TC, TISI2? Do we deposit TC? Do we perform the deposition of the TC layer? On someone. Hadi, how do you get the TC, titanium silicide? What do you have to do to be able to get that? Hadi? Will you unmute yourself and write down as well? Shana? How do you get the TC? Anyone? Hadi, mana Hadi? Sakina, right. Sakina, titanium react with silicon by rapid thermal processing in nitrogen. Yes, you have to deposit titanium, then run RTP. Okay, rapid thermal processing, we call it RTP. Rapid thermal annealing, we call it RTA. Run RTP at whatever temperature, high temperature in nitrogen to get them to alloy together titanium and silicon to form titanium silicide. Okay, let's review another one. Right, what is this? What is this layer? Oh, sorry. What is this? What do you call them? Well, okay, well, okay, well. How do you produce the well? Telaga. Any way to get the well? Faris, how do you get the well after the silicon? What do you do? Boleh unmute yourself? Lama tak ada suara. How do you run? How do you produce the well? While you are writing down, kalau you, let's say you join internship ataupun you kerja nanti kat Siltera, Infineon and Fab, you're gonna go through few weeks of training, process training, safety training, software training, process training. Process training ni you're gonna run the very same thing macam ni juga slide dia, lebih kurang. Dia akan introduce kat you daripada RCA, cleaning, wafer cleaning, wafer masuk, the whole process flow, lithography untuk apa, etching untuk apa, implant untuk apa, diffusion, CMP. You akan go through the very same training again. Okay? So sekarang you dah belajar semua daripada awal sampai integration. Then you've gone through the process already. Kalau pergi training kat Sitera intern untuk process training, semua tu jadi kacangnya. Senang je sebab you dah go through dah. Compared to others yang mungkin fresh in terms of fabrication. Mungkin the background chemical ke, for example, tak belajar subject fabrication. For example, if you talk about EE dekat USM, I think they just have like one topic dalam satu course, satu topik je untuk cover the whole fabrication. Satu topik je. Macam you're talking about process integration ni, satu topik je. But you now learn as a whole course, 487. Dia satu topik dalam satu whole course only. So that's the breadth and depth that you learn in this degree program. Okay, so something yang tak ada kat tempat lain lah, tak kat tempat lain. So you're very lucky in that sense, right? So you learn the whole stretch satu semester, the whole process. Sebab dulu bila saya training, my background was in EE. Bila saya graduate dulu saya belajar semiconductor course ni just very little when I was in Sheffield last time. Very little fabrication knowledge. Bila saya go through the fabrication training dekat Siltera tu, it's a completely new thing to me. Belajar the whole fabrication process dalam multiple training. But in your case, you dah belajar semua siap lah. So kalau you pergi front end industry, jadi you tengok implant, okay, you dah faham all the basics. Diffusion dah faham, litho you dah faham. Tinggal nak learn all the, the equipment, the job file, the recipe creation, how do you actually press that button to get things running. Tapi the basic, you've got all the basic already, right? Good. Okay, back to this. Implant. Okay, you have to implant, right? So do you have to go for low energy or high energy implant for this particular well? What is? Do you have to use high energy because you want to produce well? Okay, nak masuk dalam you want to go very deep, then you have to use high energy implant, right? So that's done. So we've covered. We have covered that. We've covered this. Okay, next. Still have time. Okay, how about this layer? This yellow thin layer below the gate. What is that? What is that layer? Thin yellow layer below the gate. What is that layer? Anyone? SecOx, huh? Do you get to see SecOx in the final device? Juara? No, right? It was already removed, isn't it? Kita introduce SecOx just to capture the defects. And then we etch with the HF, then SecOx is gone and therefore not visible in the final device. So what is that layer then? Close, study, close. Ox, your ox is close. But the first word is not. Gate ox, right? Gate oxide. So what is sit under the gate, right? So relate back to your MOSFET punya architecture kita belajar dulu, 386, the gate ox under the gate, and then source drain left and right. Okay, so gate ox. So why do you have the gate ox? What is the function of gate ox? Why gate ox? How gate ox? Buffer. Kenapa ada gate oxide in the first place? What if you don't have oxide in between? Jadi. So next, how about this layer? What is that layer? This one. What is this? Be specific. Metal apa? Yes, metal. But metal. Metal one, right? Metal one. So is the first metal layer, right? Okay, good. Next. What is this layer? Yellow color. IMD1. Good, right? Next. What is this layer? Gray ni. Layer apa tu? Almost the end if you're talking about metal 2, right? Via plug. Okay, via plug. Okay, then what is this layer? What is that layer? The orange one. Preservation, right? And then final one, last one. What is this? Why do you have this? The open area. What is that open area? Why do you have that open area? Open area though? Bond pad, right? You open for bond pad for connection to the outer world, right? Good, bond pad. Okay, sekarang you tengok kat sini, you nampak up to metal 2, right? Metal 2. Then now at least it's not that bad, it's not that obvious, but now you can see that your switching process is down below. Okay, sekarang mungkin tak nampak too obvious because it's only up to metal 2. If talking about metal 3, then you have metal 3, then you have the metal 4, then you have the metal 5, metal 6, metal 7, top metal. Then you can see that your switching takes place down here. Okay, so the core ataupun the heart of the device, in this case the transistor, lies at the bottom part. Okay, the switching, the core lah, the core process, the switching process, the gate or source drain, the channel formation, all down below. Okay, yang atas tu semua interconnect ya, metal interconnect. We're gonna learn in the next topic Monday. Metal interconnects. Macam mana dia punya, what is the role of the layers? We're gonna see the SEM cross section later on in the next topic. In the lecture notes, right? So now you can already see the whole process flow and the whole integration of the device. Okay, the device. So if you go back, you can see now the integration, what integration means, right? From this. So, and you can see all the, all the layers in the final devices now can be divided into isolations, wells, junction, gate stacks, and interconnect. The isolation to STI, mula. Then the wells, yang kita discuss tadi, well, PMOS, NMOS, and then your junction is the tip, and then the source drain for your formation, and then the gate stack is the gate and gate oxide, and then your interconnect will be the plug, metal 1, plug 2, plug 3, plug 4, plug, sampai preservation lah. Okay, sampai preservation. and then you open your bond pad for the backend industry. So the moment you have finished those, wafer to dah ready. Wafer to dah ready as a piece. As a piece, 8-inch, 12-inch, 18-inch, whatever your fab is running. So in our case, 8-inch, for example. Then you finish up to that level, and then you're gonna run your test. Okay. Test point is another thing. We call that as e-test, electrical test. Huh? So e-test is normally done. We call that as electrical test. So kalau you nampak macam post internship ataupun job as test engineer, for example, for wafer fab. So you're gonna be testing first the moment you finish your gate formation. So the moment you finish your gate, you will be testing this at this level. So this will be your first test level before you start with your interconnect. Dia akan adalah set of parameters that you have to conform to, and SPC charts and so on and so forth, to confirm that your gate is okay, your device is okay, the core of the device is okay. And then the next test, the full test, will be done the moment you finished up to this. Okay, next test. And then test dekat apa e-test yang awal dengan e-test yang last tu. Yeah, I'll come to your question kalau the field test nak buat apa. So dia akan ada apa ni? You gotta have a set of parameters at this level and at this level to show that your devices are working fine. Okay. Final one will be the complete one because you get to see the whole picture, your whole punya device performance before you pass to your customer. So your customer will be the backend lah, backend yang buat all the dicing, the packaging, letak kaki and put on the board, masuk produk, masuk laptop, masuk phones, masuk whatever, right? To consumer level lah. Sekarang kita dekat front end je. Back end will be all packaging, kemudian system integration will be, masuk on the board, everything. Right, kalau dia fail test, kena scrap terus ke? Good question. If your devices, what do you think? Can you still save? Can you still save at gate level? And can you still save at the final level? What do you think, Haziq? Or tiba-tiba your test tak confirm, then what would happen? Kalau let's say you dah finish up to preservation, you run test and it fails. Done. Habis lah, gone lah, tak boleh jual lah. Unless you are the buyer yang can buy second tier punya performance. Okay, just like solar cell lah. Solar cell kalau bila you finish the device in the factory, they will sort the device performance. Okay, so you can say let's say kita categorize as tier 1, tier 2, tier 3, assuming dalam industry normally they call it bin lah, bin number 1, bin number 2, bin number 3, whatever bins they can name in as different bin as well. But the whole idea of that is actually to sort your devices according to performance. First is the tip-top performance, second will be the second level, third level, and so on. If you talk about solar industry, then we're going to talk that in your presentation later on when I think two groups will be presenting on silicon, solar cell, and then cadmium telluride, right? So if you talk about solar cell industry, then the cells will be sorted according to conversion efficiency. For example, if you're talking about your capability is like 22%, supposed to be minimum, then it will be sorted, the cells will be sorted as 22% minimum, and then your next bin will be 20 to 22, for example, or 21 to 22. Perhaps the next bin will be 20 to 21, and then each cells in each bin will be sold separately. Kalau macam panel, then you are going to assemble these cells together as a plate, as a panel of high performance panels. Sebab semua cell sama kategori. Kemudian the second bin 2, assemble jadi satu plate, lower performance. You sell at lower price, lower price, lower price. The same goes to other, in this case as well. If you have customers that can accept tier 2 more or less, ataupun bin 2 if you like, then you still can save them by selling at lower price, something like that, right? Unless kalau dia fail, then nothing shows up on your curve, gone. Right? Nothing shows up, you don't have anything, then how do you sell? you akan jual crab lah. Jual crabs. Just rubbish. You sell wafers that are not working. Devices that are not working. So why sell? Who would buy? If you are the customer, would you buy devices that don't show any curve? Of course you won't buy, right? It's scrap and gone. So by then, just imagine how much have you spent on a single wafer. Okay, during my time, kita dah masih kan 11:30, 45 already. Okay, during my time, one of the technologies that ran in the mass production, a single wafer, 8-inch, costed around 1,000 USD. 1,000. Satu piece, 8-inch. And one pot consists of 25 wafers. So when you bring one pot to one station to another, to one equipment, you're actually carrying 25,000 USD in your hands. So that's like you're carrying 100,000 ringgit worth of asset lah. Asset negara kan. Khazanah punya dulu back then, now it's switched the next. So you bawa satu pot tu, 100,000 ringgit. So harga sebiji kereta, right? 100,000K. So 100,000. So just imagine if you have wafer breakage, the whole pot, satu pot kalau breakage, 1,000 ringgit gone, right? So kalau ada wafer breakage 4 pots, 400,000 gone. Kalau ada wafer breakage 10 pots, breakage ke vacuum loss, suddenly you spin at high speed, boom, pecah. If you have 10, you are losing 1 million due to wafer breakage. So kalau you can save the issue ataupun you detected the issue at gate, maknanya you buat test tadi, test awal, you can detect already something wrong, then you might not continue the process. But you can save already at the very front end of the process where you have not invested as much just yet, right? Tapi kalau dah invest up to metal 8, metal 9, top metal, and eventually scrap. So by then you have spent like 3 months of fabrication and hundreds of thousands of ringgit in the fabrication processes. And just to discover that they are not working due to whatever reason. So that's why troubleshooting, preventive maintenance, corrective action, 8D report, FMEA, SPC chart monitored closely are very, very crucial. Skill set, knowledge, experience come together to make sure that you are delivering what you're supposed to deliver. Okay? Kalau tidak macam ni, sampai dekat ujung, tiba-tiba you punya fat and power trip. It happens quite a number of times. Dekat kulim is supplied by no distribution instead of TNB. Habis dah metal, then top metal dah habis, then you have power trip, then wafer scrap. Then how much per wafer have you spent, and how many pots are affected, how many lots, satu lot tu satu pot lah, how many lots are affected by then? Millions of dollars gone due to power trip. Okay, so yeah, that's the operation side of the fabrication cost. Okay, so it's not only the physics, the process, it boils down to the operation. And then kalau you punya wafer tak tip-top, you cannot sell as much, so it goes to the average selling price. Ni satu lagi ya, and you have to learn ASP. You're going to learn this one later on kalau you join semiconductor. ASP, average selling price of every chip or every wafer. Okay, kalau you punya fabrication cost mahal, but eventually your performance is not, it's just so your ASP will be lower. You can only sell at lower price. And then how much is that in comparison to your cost? Can you sustain the fab then? Kalau tak boleh sustain the fab, how do you run the fab in the next 5-10 years? How do you sustain your employees? How do you sustain your operation? How do you give bonus? How do you pay salaries? ASP, relative to your cost, operation expenses. So these are not obvious yet in your case. Tapi bila you masuk internship and you kerja, then this will be a thing, right? ASP, performance of the device will determine the performance of the factory. That will determine the salary, the bonus, the whatever performance review, the annual salary increment, blah 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 blah. Right? So just to give you the reality mindset. Right. So do you have any questions? We are done with the integration. And bear in mind that this is not the real integration. as you will see in the real devices, because it really depends on what sort of devices you're working on and the configurations, how many layers, but the basics remain the same. Okay, kalau you buat MEMS, dia punya process flow will be different. You buat silicon photonics, the flow will be different. You buat MOSFET, obviously it's different. You buat FinFET, obviously it will be different. GAA FET, different. And what else? BJT, silicon carbide, GaN LEDs. We're going to see all of those stuff in our presentation later on. So that's why each group is assigned to study and explore and share and present the fabrication of different devices. So that bila you present nanti and you discuss and you ask question, you will get to see the difference between the process flow or the integration of this lecture versus cadmium telluride, SSD, gallium nitride LEDs, PERC silicon solar cells, what else? Apa lagi? All the 5 topics saya pernah lupa. Right? So you'll get to see how the fabrication and integration different from each other. Nanti you tengok, you have to, bila you nak share fabrication nanti, fabrication flow, make sure you first attach the device configuration, more or less, even though it's not the real one, the actual one in the factory, tunjuk yang configuration it looks like macam mana, macam ni, something like this. Then you can appreciate the difference between configuration of your case versus this case, your case versus SSD, SSD versus cadmium telluride, and you can appreciate. Dia tengok, oh yang ni tungsten plug dia pakai different material, oh the position dia pakai different, and then this one pakai metal lain, ni pakai metal lain, and then this one litho is not that complicated, this one is more complicated. So bila you ada all this foundation, bila you pergi industri mana pun, it will be similar except the details, like the flow, the process. Tapi dia punya foundation sama je. Patterning, litho first, then S, then nak diffuse ke, nak implant ke. That depends on the device and the industry and many more things. Tapi kalau you ada basic ni, you pergi mana-mana industri pun pretty much the same. Okay, so that's all for today. Any last question? Okay, alright. Presentation. Oh, ada cuti kan? Meeting presentation mana nanti Senin 31st. Oh, yeah. Chinese New Year. Exactly. Okay. The week after that, will it be a revision week? This will be week 15 kan? Study week. Tak apalah, kita tak ada exam. So since it's Chinese New Year, so we can have your presentation, 2 presentation in the first session on the 31st, and then Selasa cuti. Then okay, 2 more presentation. So we're done with 4, and then next Monday tu kita ambil lah 1 hari untuk habiskan. Okay, and we don't have final exam anyway, so there's no revision week per se lah. So we're gonna continue with the next Monday, 16, week 16, just to finish off another group. Okay, so that's alright, right? Tak ada issue kan? Okay. Okay then. Yeah, alright then. So any other question? Ada? 11:53 already. So if there's no question, then we are done with process integration. Then our last topic next week, next Monday, will be on interconnects, metal and interconnects. We're going to talk about the metal one and all the stuff. Okay. Then we'll be done with the course content. Then you'll be left with your assignment. That will be due on 26, right? 26, I think. Yeah, 26. And then your presentation will start on the 31st. So masa kelas yang you ada after Monday next week, Tuesday and Friday, use them for your preparation. Okay. Then we'll be done by that. All right. So thank you. Bye-bye. Take care. Assalamualaikum.